Let's walk through an example here of using that ideal gas equation. Well, you have a bubble that comes in from the bottom of the lake. The ocean or a lake usually have sources of gas that comes out from the Earth's core, and these gases, they tend to bubble up, of course, because they're less dense than water, so they're going to bubble up to the surface. In this case, the temperature and pressure initially are 8 degrees Celsius, fairly cold, 6.4 atmosphere of pressure, very high, obviously, because we're underneath at the bottom of the lake. When the bubble reaches the surface of the lake, temperature has gone up to 25 degrees. The pressure is now 1 atmosphere. Well, if its initial volume was 2.1 milliliters, fairly small volume. Now we want to know what is the volume at the time it reached the surface of the lake. You just kind of write out the conditions that we have before and after a particular process. Initially, it has a temperature of 8 degrees Celsius. This is T1, and then we have pressure 1, which is fairly high, 6.4 atmosphere. And then we have the first volume, 2.1 milliliters. And then we have temperature 2, which is 25 degrees Celsius. And then we have pressure 2 at the surface of the lake, which is just 1 atmosphere. And the question that we're asked is volume 2. Now remember that before we do anything, let's convert this to Kelvin first. We 281 and 298 kelvins respectively for the initial and final temperature. Now the question you should ask is that if you have a lake and your bubble starts from the bottom of the lake, as it goes up, we assume that the bubble remains the same bubble. So in other words, the bubble might change in shape. Here might get bigger. We'll have to calculate that volume or smaller. We don't really know. But what I want to point out here is that notice that the N, which is the number of moles of gas inside this bubble, remains the same because you basically have that same gas. So the number of particles of gas remains the same. So in other words, N1 is equal to N2 in this case. So then if you were to write out your ideal gas equation, remember that PV equals PV over NT equals to R, and that has to equal to P2 V2 over N2 T2, and all of these has to equal to your gas constant. I just said that N1 and N2 are equal to each other. That means that they will cancel out. So then we're left with just P1 V1 over T1 equals P2 V2 over T2. We're trying to solve in this case for volume 2. So I'm going to separate this out from the rest of the equation and write this out. Okay, so it'll be P1 V1 over T1 times the inverse of this value, which is then just T2 over P2. Okay, so I'm going to plug these numbers in here, starting with my P1 V1 T1. Okay, so the P1 is 6.4 atmosphere. The volume 1 in this case is 2.1 milliliters. Temperature 1 in this case is 281 Kelvin. Okay, so that's appropriate units. And then the second factor, T2, is 298 Kelvin. And then I have 1 atmosphere as the second pressure. Now you notice what happens is correct units cancel out, kelvins and atmosphere, leaving me with just units of milliliter. Yeah, I want to point out that if you were to calculate it, you should get a number of value of around 14.3 milliliters. Okay. Okay, let's take a look at question 6 in topic set 5. This question gives us some information about a gas, and then it says we're adding some more gas to that same container, and then the temperature goes up to 50 degrees Celsius, and pressure also goes up. The question is how many moles of gas were added. Okay, so let's kind of draw this out a little bit. So we have a container that originally have some gas in it, and the amount of gas is 1.5 moles. Temperature was 25, and pressure is 400. And what we did is we let some more gas in here. The amount of gas has increased, and so we don't know by how much. So the number of moles in the second condition is unknown, but the pressure now in the second condition is 804, and the temperature in the second condition is 50 degrees Celsius. Okay, so you can write these ones as the first condition, T1 and N1. All right, now you can see that once we write it down in terms of those ideal gas variables, it becomes clear that we need to use one of those ideal gas laws, variations. So we can start with just the PV equals nRT, which can be written as PV over NT equals R. And I like to write it this way because then what that means is that P times V over N times T is equal to a constant always, which means you can write it in two different conditions. So equals to P2, V2, N2, T2. And they tell you a constant volume container, so that means volume doesn't change in the two conditions. So V1 and V2 is the same, so we can cancel that out from the expression. So to figure out the number of moles of gas that's added, that means we need to take the difference of what we have at the end, N2, minus what we have at the beginning, which requires us to calculate N2 here using this relationship. So let's rearrange that expression, okay, just to do a cross multiplication. So your N2 would be on this side, and then you just bring everything else to the other side. So the P2 and the T2 would remain there, and then the N1, T1 becomes the numerator because you do the cross here, and then the P1 becomes the denominator. And then it's just a matter of plugging in the values that you have. P2 is 800 torr. Now notice I don't need to change this to ATM because I have a P1 here at the bottom in the denominator that's also going to be in units of torr, so I can cancel that out. N1 is 1.5 moles. Now temperature though has to be done in Kelvin because that's how the gas relationships are observed. It's only in units of Kelvin. So the T1 is 25 degrees, so it has to be 25 plus 273 Kelvin, and then T2 50 plus 273 Kelvin, and then pressure 1 is 400 torr. Okay? And you can see that the units torrs and kelvins cancel, so you're left with number of moles as the final unit, and the answer ends up being 2.7678 moles. Now remember that's N2, so the number of gas added is going to be N2 minus N1, so we're going to take 2.7678 moles minus 1.5, and that gives us 1.2678 moles, or if we round it, it'll be 1.27 moles. So now what I want to do is just work a problem of calculating density of carbon dioxide here at 0.99 atmosphere and 55 degrees Celsius. Equation, or this expression for the density of a gas, which is just Pm over RT. And we basically, it's just a matter of plugging this particular numbers, the information you have, into that equation. So you have 0.99 atmosphere, you have a molar mass, which in this case of CO2 would be just 44 grams per mole. That I get from the periodic table. R is 0.0821 liter atmosphere in this case over mole Kelvin. And then lastly we have temperature, which of course in this case has to be expressed in Kelvin. So then we have 55 plus 273 Kelvin. And if you look out at all the units, they should cancel out to give you the appropriate units at the end. You see what's left is grams and liter, grams per liter, and that's a unit of density, of course, mass over volume. So if you were to actually make that calculation, you should get a value that's 1.618 grams per liter. One thing I want to point out is that the density of this gas is fairly low in comparison to a corresponding liquid or solid. So for example, here's the density of the CO2 in the gas form, grams per liter. If you look at the density of solid CO2, which is of course what we also call dry ice, you'll find that the density is around values of 1.5 grams per milliliter. And as you can see, there's a lot more mass per a much smaller volume in this case. So it's a lot more dense in comparison to the gas. So that's something to pay attention to as far as the density of gases in comparison to the density of the condensed phases, solids, and liquids. Let's work out this example gas sample at 0 degrees Celsius and 1 atmosphere with a mass of 3.94 grams, and they want you to calculate gas density and the molar mass. So density, just like anytime you calculate it, requires you to divide the mass over the volume of the substance, and we're already given both those numbers. So let's do 3.94 grams over 2 liters, and our answer ends up being 1.97 grams per liter. Now, molar mass, remember, is the mass of 1 mole of a substance. So if you want to get it, you're going to have to take the mass of a substance divided by its number of moles, which has the symbol N. To get the number of moles, we're going to need to think a little bit about the situation that we're given. We were told that the gas is at 0 Celsius and 1 atmosphere, which is our STP condition. And at STP, 1 mole of a gas is going to have a volume of 22.4 liters. So we can use this as our conversion factor, either that or that. In this case, since we're trying to get to the number of moles in our calculation and then later on divide mass by it, we should first use that conversion factor for STP, which is 1 mole in
every 22.4 liter, and then try to figure out the number of moles in 2 liters of the gas. And if you calculate this out, you would get 0.089287 moles of the gas. And then it's just a matter of plugging that back in to calculate the molar mass, which is 3.94 grams being the mass, and the number of moles that we just calculated. That should give us 44.1 grams per mole.